we look at this and we go, are we at the optimal value yet? And we'll say, well, no, we're not, because we still have this negative 10 in the Z row. And that means that we could improve the value of the objective function. Once there are no negative values in the Z row in equation 0, that means we'll have found our optimal value. So we have to go through the process again. And I'm hoping you're getting good at it. So we look at the Z row, we look at the coefficients there, and we pick the one that's the most negative, and that's negative 10. So that's under x2. So this x2 is going to be coming into our basis. Now I have to figure out what to take out. And so we use the minimum ratio test, and we have 2 divided by 0 is, there's no limit there. On this, on equation 2, we have 3 divided by 1, so we get 3. Now equation 3, we get 2 divided by 1 is 2. So this minimum ratio test, it's the most limiting. And so it tells us that we have to take x5 out of the basis. Again, you can look at this graphically, and it can explain to you that, well, let me just convince you. Where are we? We're at this point here of x1 is equal to 2 and x2 is equal to 0, and we're looking at how far could I go. Well, I could move it to 2, which would still be the feasible region, but I could move it to 3, which is that vertex right there, but notice that that's not in the feasible region, so I can't do that. And so that's why I take the minimum. I'm taking, it's the one where, okay, so that's great. So I now know that I'm taking x5 out of the basis and I'm putting x2 in. Now I still need to do my elementary row operations, so to clean things up. And so I need to make sure that I have zeros in everywhere above this pivot point that I have boxed in red. So I look at, let's look at the Z row. I have a negative 10 there. What can I do to equation 3 to help me get rid of that negative 10? I'll take equation 0 and add 10 times equation 3, and I'll be good to go. Next, I'm okay with equation 1 because it already has a 0. My coefficient's already 0 there. And I look at equation 2 and I say, I need to, all I have to do is subtract equation 3 from that and I'll be good to go. So I do that elementary row operations, I do that math, and here's my updated simplex tableau. And again, I should be able to look at it and figure out what all my variable values are. It tells me that the value of z is equal to 50, because the right-hand side over here tells me that z is equal to 50. So now I can go in my non-basis. What are my values that are 0? Well, the ones that aren't in the basis are x3 and x5. Those values are 0. Note that they have non-zero coefficients also in the z row. Then we have our basis values and our basic variables, and now we got to figure out what their values are. x1 is equal to 2. Is that true? Well, let's see. x1 plus x3, so this is a 1 times 0, so that means x1 has to be 2. And then we look here, x3 is 0 and x4 is 0, so we have, x3 is 0 and x5 is 0, so 1 times x4 has to equal 1. And in the last equation, equation 3, we have x2 plus 0 has to equal 2. So x2 is equal to 2. And graphically, what point are we at? Graphically, we're saying the optimal point is at 2, 2. What does x4 equal 1 mean anyway? This slack of 1 in this particular constraint is where the x4 equal 1. That's what it's representing. So there you go. There are some more ideas that you need to learn to be more sophisticated about the Tableau and all the different cases you can have. But I'll go over that in lab with you. Happy simplexing.